Hello everyone. So I'm making this video because I want us to do some more practice problems and address this question right here. What is the difference between the derivative and the slope of the tangent line? So essentially, they do sort of mean the same thing as we've discussed in class. When you hear derivative, you should be imagining that you're dealing with the slope of a tangent line. And you could also think of that as the instantaneous rate of change. As well as if you hear slope of tangent line, you should think, okay, I'm going to need the derivative. If you hear instantaneous rate of change, you should think, oh, I might need the derivative. Because all three of these are representing the same thing. But the small difference is that if you're being asked for the derivative, this is representing the slope at any point on the curve. So this is more of the general formula that we had discussed before. And it means that you'll probably, in many cases, have an answer that still has a variable in it. So for example, if f of x is x squared, the derivative f prime is 2x, and you can leave it like that. You have found the derivative. The slope of the tangent line, which we know means you're dealing with the derivative, but in many instances, when we phrase it like this, you're also going to be asked to find it at a specific point. So it's like the derivative formula, but plugging in your x value might be an extra step. So for example, you might be asked to find the slope of the tangent line to y equals x squared at x equals 4. And that's when you're going to say, okay, well, if y equals x squared, y prime, find your derivative, but then you're going to plug in the x value to get a value that looks like a slope, because 2x does not represent a specific slope. Slopes are constant numbers. So if you let x equal 4, you're going to get y prime equals 2 times 4, which is 8. And that's more of an answer that you would be giving, right? This is how you know you're done, is if you plugged in your value. I'm just going to leave this here. So that's an example for slope of tangent line. Usually we have a specific location. And similarly, instantaneous rate of change is going to be very much like the slope of the tangent line, because usually you'll be at a specific location. So you will still need your derivative, because again, they are all connected, but plug in because the rate of change at an instant is asking how much is the steepness of the curve changing here, and you should be given an x value to locate where we care about. So if you were asking for the instantaneous rate of change, Or maybe a better example is like an instantaneous velocity or an instantaneous acceleration. You're like, okay, I'm going to take my derivative and I should have been given an x value. So if they say like add x equals 2 for the same function, you would just take your derivative and plug in 2. And in this case, you would get 4 because the derivative is 2x, plug in 2, and 2 times 2 is 4. So these are specific, usually. And in the very, very beginning, we were playing with questions that were not specific, and I was asking you to find the slope of the tangent line, but the one detail I started adding was find the formula for the slope of the tangent line, and that's what the derivative is. This is general. Okay. But they are all connected. They are pretty much synonyms. It's just that in the context of the problems, this is kind of how you'll see them differ. So let's look at some examples. So you might be asked, what is the derivative of g of x equals 5x to the 9th minus 3 over x squared plus 1/2. So I'd like for you to try and find the derivative of this. Go ahead and pause your video. And when you think you have it, you can resume to check my answer. All right, so if I'm trying to find the derivative, that means I'm looking for g prime of x. And there are a couple of ways you could find the derivative of this. You could go by definition, which is the limit as h goes to 0 of g of x plus h minus g of x all over h. You could do this, but with this being the 9th power, and I also have like x in the denominator, this feels like it's gonna get a little messy. So what I'm going to utilize instead is the rule that we just came up with last week, and that is the power rule. So remember, the power rule is saying if you have a number times x to any power, then the derivative would be bringing down the old power and multiplying it to your coefficient. So that's how you're going to get p times a. And then we subtract 1 to get our new power. So that's how we get that. And this was a pattern that we observed just by looking at a bunch of different derivatives from this form. And it's like that kept happening. So let's use it here. Now, in order to use my power rule, I need to know that everything can be thought of as a number times x to some power. Clearly, this is good. So I can just do my power rule if I wanted to. But my next term doesn't quite look like a number times x to some power because I have an x in the denominator. This is a number 3 divide by x to some power. So I'm not quite thrilled about this. And I want to ask myself, can I rewrite it? Can this term be written? The answer is yes. I could think of this as -3 times x to the -2. Negative exponents allow me to move my base. And once it's in this form, it looks good because again, it can be any power. It doesn't have to be a positive number, doesn't even have to be a whole number. Any power works. And so if I rewrite it, it's good to go. And then plus 1/2 that is a number times x to a power because it's x to the 0. So that means I'm all ready. And my answer should be, bring down the 9 times 5 will be 45, x to the subtract 1 to the power. Then I have -3, and the -2 is going to come down and multiply, so I'm going to get plus 6x to the subtract 1, I'm going to get -3. And then the plus half will vanish. So this is my derivative, and that's all I have to do, because again, the derivative is asking for a general answer. And this is general because I haven't picked an x location. Right? It works for any x. Done. Let's do another one. Derivative of h of, let's do a different variable. Let's do h of t. So pause your screen and try it, and then when you're ready, you can resume. Okay, so assuming that you did that, if I'm trying to find the derivative, that's going to be h prime of t. Doesn't matter if it's t's or x's, right? All I did was change the name of the variable, but we're going to treat all input variables the same. So let's like write a note here. Input variables treated the same. X or T or W or anything, right? It doesn't matter their name. So just the fact that you see a T here, you don't need to get nervous and go, oh no, I don't have an X. The T is the X. We sometimes get very stuck on the fact that it's always X and Y. That's not always going to be the case. So it's good to do examples like this. Right, but if I look at this, yeah, that already looks like it's in the right form for a power rule. So I'm going to go ahead and use it. So 12 is going to disappear because that's just a constant. And then I should get -9t squared plus 4. Again, I'm done. This is the derivative of h. Let's do one more. So go ahead and try this one, pause the video and return when you're ready. All right, so to find the derivative of y, which if you notice, I've already mentioned this a couple times and you've seen it before, but because this isn't an f of u like function notation, it doesn't really make sense to write something like this when we're just having y, but what people usually do is just put the prime tick on the y, and that still signifies that you found the derivative. So y prime equals, and now I want to try to take the derivative, and I'm asking myself, can I use power rule here? Because that would be so much nicer. And the only one that looks a little concerning is this one. but I can rewrite this as u to a power instead of a radical. This would just be the 1/2. And now I'm ready to use my power rule pattern. And we should end up with 22u minus 1/2, because I bring down the 1/2 and multiply it to this negative 1/2 u, but now I have to subtract 1. Well, 1/2 minus 1, think of 1 as 2/2, because I'm already trying to get a common denominator. I know that if I'm subtracting anything that's a fraction, I need a common denominator. This is going to be negative 1/2. So that's my new power. Plus 15u to the 4th. Done. All right, so now we're going to try a question like this. And we should immediately, before we jump into things, think about what they're asking us for. So this question that says, find the instantaneous rate of change, that's what I'm being asked for. But when we hear those words, our brain should be thinking, derivative? Because we know that these are connected. But I'm putting question marks around here because I am pretty sure that that's not all I have to do. How do I know? Well, just the wording of instantaneous rate of change is hinting that I probably want a specific answer, not a general answer. And if I keep reading, I see that they did give me a specific location. So I know that, yes, I'm going to take my derivative, but I'm not going to be done. When I take the derivative, I'm going to have to plug in whatever value they gave me, which is 5/2. Let's go ahead and try it. Pause and then resume when you're ready. Okay, so I know I'm trying to find the derivative, so I'm going to look for f prime of x. Put this in a different color. It's a little different. F prime of x. And this looks like I can use power rule, so I'm going to get 6x squared minus 8x. Great, but I'm not done. This is not the final answer. So just beware, like, don't be like, oh, I'm finished and move on. You still have to think of, but this is general and I'm looking for specific. So please don't forget to plug in your value. That's the difference here. In the other questions, if they're just asking for the derivative, you're done. But if they're asking for instantaneous rate of change at x equals anything, you're not done yet. So now I'm just going to go ahead and plug in my value 5/2. This is going to be 6 times 5/2 squared minus 8 times 5/2. Okay, so this should be 6 times 25/4. That's why I like fractions, because you can do this in your head. If you square a fraction, you're just squaring the numerator and the denominator. Minus 8 times 5/2. Okay, so this is looking nice. I can simplify here. 4. So 3, this will become a 2. So I'm going to get 3 times 25 is 75 over 2 minus 4 times 5, because that's 1, 20. And I can simplify this pretty easy, because 20 over 1, if I multiply both of these by 2, I'll get 75 minus 40 over 2, which is 35 halves. Then I'm done. Let's try another one. All right, so I'd like for you to pause and try this one, and then resume when you're ready. We'll go over it together. Okay, so if I look at what I'm being asked for here, I'm trying to find the slope of the tangent line. Slope of the tangent line. And when I see this, I'm thinking, okay, I'm going to need the derivative. But I want to keep reading. I know it's not going to be as simple as that, because the context is probably asking me to find it in a specific location. And I can see at the end it does give me. So I'm going to find the derivative and then plug in t equals 0. That's all I got to do. So y prime is what I need. So I'm going to make note that 4t is good, but this middle term does need to be rewritten if I want to try to use my power rule. Otherwise, if I can't use my power rule, I have to do it with the definition way. So I'm going to try to rewrite this. So again, this is a radical. I know that this can be rewritten. So t to the 5th is still t to the 5th, but the cube root means that it's the 1/3. So y prime can be found with power rule. Yay. And we're going to get 4 plus 5/3 t. So 5/3 minus 1 will be minus 3 over 3, and that's going to be 2/3. So this should be my new power, minus 1. Okay. And now I'm ready to plug in my value. So y prime is 4 plus 5/3. Plug in 0. I'm gonna put on the side here that I'm plugging in 0. I should note that, right? And so 4 is going to be 4. 5/3 times 0 to the 2/3. Well, if we think about that, 0 to anything, as long as it's not, well, actually, you know what? We should think about that a little bit. So if I had 0 to the 1st, that'll be 0. If I had 0 to the 2nd, 0 times 0, which is 0. If I had 0 to the 3rd, right, we can see that that's going to be 0. Okay. But if I had 0 to the -1, that would be 1 over 0. 0 to the -2 would be 1 over 0 squared. 0 to the -3 would be 1 over 0 cubed. And all of these situations are not good, right? So when I said 0 to the anything, I had to step back for a second, because negative exponents are not included in that, right? We would have an issue here. So it's not quite 0 to the anything. But as long as it's not 0 to a negative, and it's not 0 to the 0, because both of these are not good situations. If it's any positive exponent, though, we should be fine. Because you can take the cube root of 0. You could take the square root of 0. Radicals are fine. So when I see 0 to the 2/3, I'm like, yeah, that's just going to be 0. So I'm essentially going to have 4 plus 0 minus 1, which is 3. That is the slope of my tangent line at t equals 0. Awesome. Okay, let's do one final question. All right, so I want to look at this question because you might already be familiar with this, but let's talk about it a little bit. There's also a separate video that goes into more detail about objects in motion. So you have a moving object, and you see words like displacement and velocity, and this is the time, right? This question is pretty much no different than the other questions. It's just that we're in a applied context, right? We're using all our skills to study a real life, quote unquote, object, right? This is like a physics application. I just want to talk about it a little bit. But please go check out that other video that goes into more depth. So if you have the displacement, this is really just like the position. And it's specifically the position away from where you started. Okay. It's going to be given in meters by this function. Cool. And you're being asked to find the instantaneous velocity. Okay. Well, it will help if I tell you that the units of velocity will be meters per second. So if you think about just the units, this should tell you exactly what you're trying to find. So when we see meters per second, this is a ratio. And if we think of, okay, what did we know was given in meters? The displacement was meters, and it was this formula. Okay, so it has something to do with this formula. And we have seconds, which is the time, underneath. Now, the way this is set up, this will make more sense, like I said, if you watch the other video, but if you just briefly think about it, if an object is moving with a velocity, okay, if you're moving, you're not going to stay in the same position. Your position is going to change. So if I have a ratio, and the ratio that I'm dealing with is position over time, which I know is changing, this is really the ratio of change. Or in other words, it's a rate of change. So velocity is just a type of rate of change. And they're asking me for the instantaneous rate of change. And what do we think of when we hear instantaneous rate of change? The derivative. Woo. And so hopefully it's clear how this is really just like the other problems. I'm still going to find the derivative, and then I'm going to plug in my specific value. And again, it's the rate of change of position, right? So I am taking the derivative of the only formula that I can possibly take the derivative of. So even if you weren't sure, it's like you kind of only have one option. So I'm looking for S prime of t. Oops, let's maybe put our work in a different color. So I'm looking for S prime of t. Now, if I look at what I have here, this is not in the form for power rule, because I need everything to look like a number times t to some power. Why does this not look like we have that form? Because right here, I have t times another t, right? It's t squared minus 5, but I'm not adding up different terms with t. I'm multiplying two terms with t. So this isn't looking good. But is it possible to rewrite it so that it does look like a number times t to the power plus another number times t to the power? Pause and try rewriting this. Okay, so hopefully you thought about it. And this can be rewritten if I just distribute. That should be okay, because then I'm going to have t times t squared, which is t cubed, minus 5t. And now this is totally ready for power rule. So that's kind of nice. Right. So go ahead and try and finish this question. Pause, and when you resume, I'll go through it. All right, so my derivative of t cubed minus 5t should be 3t squared minus 5. So there's the general derivative, but again, I didn't even write it over here, but I know I'll have to plug in t equals 3 halves. So if I do that, I'm going to have s prime of 3 halves equals 3 times 3 halves squared minus 5, which is going to be 3 times, so 3 squared is 9, 2 squared is 4, minus 5, so that's 27/4 minus 5. And again, this is quick and easy to combine. It's going to be 27 minus 20 all over 4, which is 7/4. And this is it. But the one extra thing we want to add on here are the units. And I already gave you what they should be. It's going to be meters squared. Sorry, meters per second. Ta-da. And it actually, I think I kind of like it better written like that. Okay, so I'm hoping that this kind of clears up the difference between when you're being asked just for the derivative and when you're being asked for the derivative at a value. If you have any questions, please make note of them, and we can always talk about it in student hours or the next time I see you. But thank you for watching. Have a great day. Bye.